So if f of x equals little f of x over g of x, then this is an expression, the derivative of f of x. I'm going to write this a little bit more simply. Okay, if f of x equals u over v, then f prime of x equals u prime v minus u v prime over v squared. Where u or v are could be considered two other functions. Okay, so let's try this once, and then I'd like to show you where this comes from. And again, I won't ever ask you to derive this yourself, but again, I don't like to show you things that fall from the sky, so this one won't take us too long. Okay, so find d by dx of x cubed plus 7 over x. And by the way, this notation, some of you guys have asked me about this before. The line that would sort of come before this is that y equals x cubed plus 7 over x. And so I would say find dy by dx, and then I'm plugging in for y this expression, because this is what y is equal to. Okay, so find dy by dx, which is that, because y equals that. Okay, so when you see something like this in brackets like that, this would have been the original function. Okay, so when we are doing something like this, just like in the product rule, we want to assign what's u, what's v. Let's find all of their derivatives. Okay, so in this case, u is x cubed plus 7, and u prime would be 3x squared. And v is x, so its derivative is 1. Okay, so dy by dx is, I'm going to write that out first. And I find this, particularly when I'm using the product law, because there's sort of so many pieces, a really good strategy, because I have all my pieces off to the side, and then I have a place to put them. Okay, and here order does matter, because we're looking at subtraction in the numerator as opposed to addition. Okay, so u prime 3x squared times v times x minus u x cubed plus 7 times v prime times 1 over v squared, x squared. Or I should say, the bracket, sorry, should go here. Okay, and now we would simplify this. Collect like terms. So we're going to get 3x cubed minus x cubed minus 7 over x squared. Okay, and then you can, I don't have room here, but I'll simplify that over here. Dy by dx equals 2x cubed minus 7 over x squared. Okay, so let's talk about why this is the way it is. So if you want to write this down, you can. If you want to just sit back and enjoy and take it in, you can do that too. Okay, so I'm going to just, to simplify things a little bit, take out the function notation. Let's just say that f equals u over v. Just to make things a little simpler. Okay, and now what I'm going to do is I am going to solve for v so that I don't have the division. So I'll just multiply by v on both sides. And I'm going to get that f times v equals u. And I'm going to now use the product rule to find the derivative of u. Okay, because now this is a product, so I can find the derivative of u since this is a product. Okay, so u prime is f prime v plus f v prime. So far, so good? Okay. Now, what we really wanted out of all of this was we wanted f prime. That's what we wanted. So what I'm going to do now is I'm going to isolate f prime. Because the whole point of this was to figure out why the quotient rule works the way it does so that I can figure out how to find the derivative of f. Right? When my function is the quotient of two other functions, how do I find its derivative? So I'm going to go and isolate that. Okay, so that means I have to subtract f v prime from both sides. Okay, so I'm going to have u prime minus f v prime equals f prime v. Okay, and what do I have to do now to isolate f prime? What am I doing to f prime? Yeah, I'm multiplying by v, so I got to divide by v. I'm going to do that over here as well. So I have divided by v. So I'm almost there, except that originally f was equal to u over v. And I still have an f in here. I don't really want that. So I'm going to take the u over v and sub it in for f. That's going to be my next line. So I'm going to get u prime minus u over v times v prime over v equals f prime. Okay, so I've subbed, f was equal to u over v, so I subbed in a u over v for f. Okay, and now what I want in this numerator is I want a common denominator, because right now the u prime is just over 1. And this u times v prime is over v. Okay, so between 1 and v, the LCD is v. So I need to multiply this by v over v. And what I'm going to get is u prime v minus uv prime over v equals f prime. Then I can bring this down. And then I have my quotient rule. Because it's v times v, which is v squared. Okay? So that's where this comes from. have to do the product law to be able to get, or the product rule, rather, to get the quotient rule. Okay, so now let's practice it a bit more. So I'm going to go back. And if we look at this next example, there's a number of ways that we could do this one. We could just use the power rule to do this, because we could write all of these terms using negative exponents. So that's one option. But we could also write these terms using a common denominator. So that's another one. So we're going to try doing it both ways. Okay? So if we use the power rule, we would want to write y as with all of these terms as negative exponents. So it would be, instead of 12 over x, 12x to the negative 1, and then minus 4x to the negative 3 plus 3x to the negative 4. Okay, and now we just use our power rule. So we multiply whatever the coefficient is in front by the existing exponent, and then decrease it by 1. So this is going to become negative 1 times 12 is negative 12x to the negative 2. And then negative 3 times negative 4 is plus 12x to the negative 4. And negative 4 times negative 3 is minus 12x to the negative 5. Okay, and then we're going to want to write those exponents as being positive again. So this is now going to be negative 12 over x squared plus 12 over x to the 4 minus 12 over x to the 5. And then let's also, oh, sorry, this should be y prime, my bad. Let's also try and get a common denominator. So between these three denominators, x squared, x to the 4, and x to the 5, what's the least common denominator? X to the 5, that's right. Okay, because 5 x's. We have to have 5 x's in there. So here we're missing 3, right? Because we only have 2. So we'd have to multiply this guy by x cubed over x cubed, and this one by x over x, to get that x to the 5. That doesn't look like 3, my apologies. It's a little better. So this is going to become negative 12x cubed over x to the 5 plus 12x over x to the 5 minus 12 over x to the 5. And then we can write that over a single denominator if we want. And also in the numerator, there's this common factor of 12. So I could factor that out as well if I wanted to. Not a bad idea to do because sometimes things simplify. In this case it won't, but maybe it will. Oh, this was y prime. That's the notation, sorry, that we were using. Sometimes I lose track. And then what we'll have in the numerator is x cubed. And you guys remember when the first term is negative, you factor the negative sign out as well? Yeah, okay, good. So x cubed minus x plus 1. Okay, so that's y prime, using the power rule. Okay. Now, if we wanted to use the quotient rule, we would have to do that step of the least common denominator first. okay? So that we can actually get a quotient. Okay, so we had y equals 12 over x minus 4 over x cubed plus 3 over x to the 4. Okay, so here the LCD would be x to the 4 in the original function. Okay, so I've got to multiply this one by x cubed over x cubed. I don't have a lot of space here. Well, are you guys okay with, have you done this enough that we can do this all in one step? Yeah, okay, sweet. So if this is all over x to the 4, this is going to be 12x cubed minus 4x plus 3. There we go. That's why. Okay. There we go. Okay, so now we have the function written as the quotient of two other functions. Okay, so my u is the numerator, 12x cubed minus 4x plus 3, which means u prime is 3 times 12 is 36, x squared minus 4. And v is x to the 4, which means v prime is 4x cubed. Okay, so quotient. There we go. Using the quotient rule, y prime is u prime v minus uv prime over v squared. Okay, so let's see what that is. 36x squared minus 4 times v, x to the 4, minus, ooh, I'm running out of space here. Okay, 12x cubed minus 4x plus 3 times v prime is 4x cubed over v squared is x to the 4 squared. And this has quite a bit of simplification. Yeah. So you can see, I mean, there's often multiple ways of doing things, right? In this scenario, probably a lot more straightforward to do it the first way. Okay, but I'm going to show you several. And firstly, I want to show you several to show you that this does in fact work. And also, we're going to practice this because just like in the product rule, where sometimes you could do the same thing just by expanding first, you don't have to use the product rule, there will be scenarios where you have to use the quotient rule. For example, when one of the polynomials, not polynomials, when one of the either numerator or denominator is not either a polynomial function or something that can be written as x to a power, x to an exponent, right? Then we can't use the power rule, okay? So we don't have another option. Okay, but let's do some algebra here. Simplification. So y equals, we got to distribute here. So 36 times x squared times x to the 4 is 36 x to the 6 minus 4x to the 4. And then minus 12 times 4 is 48. x cubed times x cubed is x to the 6. And I've got minus, so that's plus. 4 times 4 is 16. X times x cubed is x to the 4. And then minus plus is minus. 3 times 4 is 12. X cubed over x to the 4 squared is x to the 8. It's a good chance to practice your exponent laws. It'll be a miracle if I don't make a mistake today. And then let's see, we've got negative 12 x to the 6. Okay, that's good. Plus 12 x to the 4. Minus 12 x cubed over x to the 8. This is why factoring is important. So I can factor out a 12x cubed, or a negative 12x cubed. Oh, this should be y prime. My bad. There we go, there's the mistake. But I caught it myself, so then it doesn't count, right? Okay, so numerator, common factor, negative 12x cubed. And we have x cubed minus x plus, no, yes? Plus 1 over x to the 8. And then some of these x's cancel. 3 of them. Negative 12 times x cubed minus x plus 1 over x to the 5. There we go. Is that the same thing we got before? I'm crossing my fingers. Yes? Okay, good. That's okay. You just got to get there. Doesn't matter how. Okay, good. You scared me there for a sec. Okay. Does anyone still need to write something down? I skipped ahead there. Okay. Okay, so these last two are pretty straightforward. So we're just going to kind of go through them quickly. And then I'm going to give you guys time to do some practice. Okay? Nothing really to do here except for some quotient laws, quotient rules, not law, rule. Okay, so again, we're going to assign u, which is x squared plus 4x minus 1. And in fact, this is another example where you have to use a quotient rule, right? Because nothing factors here. If you just had an x in the denominator, you could actually divide each term by x, and then, yeah, you could use the power rule. But because it's a binomial, you have to use the quotient rule. There's nothing else to do. So u prime is going to be 2x plus 4. And v is x minus 6. So v prime is 1. Okay, so f prime of x is u prime v minus uv prime over v squared. And that is 2x plus 4 times x minus 6 minus u x squared plus 4x minus 1 times 1 over x minus 6 squared. Now we've just got some simplification to do in the numerator. So expanding this out, we're going to get 2x squared minus 12x plus 4x is minus 8x minus 12. No, 24. Okay, and then minus x squared minus 4x plus 1 over x minus 6 squared. And then we should combine like terms and check if anything can factor, because occasionally you will get a if it's factorable, there might be a factor of x minus 6 in the numerator as well, right? So we got to check for that. So that is, what is it? X squared minus 12x minus 23. Not the case this time. Over x minus 6 squared. You can leave that factored. In fact, it kind of tells you more when it's factored than when it's not. Why does it tell you more when it's factored? What does it tell you about? Yeah.
Because we know it's simplified, it can possibly be.
It is simplified, but it actually tells you something about the function when it's in factored form. If you have a factor of x minus 6 in the denominator, yeah.
Doesn't it tell you where it's differentiable?
Exactly. Yeah, x can't equal 6, right? It's not differentiable at x equals 6, because if you put a 6 in for x, then the derivative is going to be an undefined value, which means that this function is not differentiable when x equals 6. Okay? And actually, if you look at the function, you should be able to tell that from the function as well, because there's a factor of x minus 6 in the original function too, right? But I would leave denominators factored in derivatives in general, because they do give you information about the original function in terms of where is it differentiable and where is it not. Okay? All right. Nice. One more. Given f of x, find f prime of x. Okay, so same drill. U equals the square root of x, which is x to the 1/2. Okay, that means u prime is 1/2 x to the negative 1/2. Okay, and v is 1 plus 2x, which means v prime is 2. Okay, so to get f prime of x, that's going to be u prime v minus u v prime over v squared. Okay, so let's see what that is. U prime is 1/2 x to the negative 1/2 times v times 1 plus 2x minus uv prime. So u is x to the 1/2. V prime is times 2. over v squared is 1 plus 2x squared. And now there's a bunch of simplification to do. And by the way, the reason why when I found those parts u prime, v prime, or specifically here u and u prime, I left particularly u prime as a negative exponent and not a radical, is because I was thinking a little bit ahead and I knew that I was going to have to do some distribution here, which meant I knew I was going to have to use my exponent laws. Okay, so that's another thing where if you don't think ahead, it's just experience, right? And the more you practice, the more you'll be like, oh yeah, I have to do that, so it makes more sense to leave it as a negative exponent because then I'll have to go back, right? But if you do switch it to radical, no big deal, just switch it back, okay? All right, so if I expand this, I'm going to get 1/2 x to the negative 1/2 plus half times 2 is 1, and x to the 1/2 times x to the 1 is x to the 1/2 minus 2x to the 1/2 over 1 plus 2x squared. Okay, now at this point, I would probably start thinking about, this is a fraction, this belongs in the denominator. So yeah, I'm going to start to put this in the denominator because then I also have to start thinking about, this is going to be a fraction plus non-fractions, common denominators, if I want to simplify this. Okay, so where are we at? F prime of x equals, so I'm going to write this as 1 over 2 times maybe the square root of x at this point, because I don't think I'm going to have to do anything else with it. And then x to the half minus 2x to the half is minus the square root of x over 1. Maybe I'll do that so I can see the denominators. Over 1 plus 2x squared. Okay, so what's the common denominator here? Between 2 root x and 1. Yeah, 2 root x. So I'm going to multiply this by 2 root x over 2 root x. And I'm going to get 1 minus 2x over 2 root x over 1 plus 2x squared. Because root x times 2 root x is 2x. Okay, and then I can bring this down. And so my final answer is f prime of x equals 1 minus 2x over 2 root x times 1 plus 2x squared. Okay, and one of the reasons, again, why it's important to write these things simplified with, you know, like, for example, the 2 root x in the denominator, is it really helps you to see where these functions are differentiable and not. Okay, so when I'm looking at this, I can see, and again, this takes some experience, that it is not differentiable when x equals negative 1/2, because that is going to produce a 0 in the denominator. But in fact, that doesn't even matter, because from this factor here, x has to be greater than 0, and it can't equal 0. Because if it equals 0, the fact that this is in the denominator means that I'm going to put a 0 in my denominator. Okay? Now, the function itself, the original function is defined at 0, okay? Because here the radical is in the numerator. So I'm allowed to have a 0 here. But I can't have it in the derivative, because in the derivative, the radical's in the denominator. So what does that tell me? The function's defined at 0, but there's no derivative at 0, which means it's probably going to be an endpoint. Okay? Now, I haven't looked at this on a graph. So we're going to do that right now. And if that's not the case, then I'm going to look a little bit like an idiot. But hopefully that is the case. Let's take a look at what happens. My guess is that that's what's going to happen. Let's see. We're looking at the original function here. So what was it? It was the square root of x divided by 1 plus 2x? Was that it? Okay, let's see. I'm kind of nervous. There you go. Okay, that point 0 is an endpoint. Okay, and again, for what we're doing right now, I'm not going to ask you about that right now, specifically. I may ask you stuff about, because you know this is kind of the point where our quiz is covering up to this point. Okay, you do need to know that if there's an endpoint or like a corner, that there's no derivative there. Okay, from a graph. But I won't ask you, here's the derivative, tell me what's going on in the graph. I'm not going to ask it from that direction. Okay, I may give you something like this. Here's f of x. We did some like this, and I gave you some in your homework. Draw approximately f prime of x, right? So how do you do that? Just a reminder. And tomorrow's a review day, by the way, so we'll have time to look at these as well. But how do you approximately do that? Well, look at where the function is at a max min, because then the slope is 0, right? That has a slope of 0. That has a slope of 0, which means the derivative is 0, because the slope of the tangent is 0. Okay? And then look at, here the slope is positive. And here it's sloping in the negative direction. And then here it's sloping in the positive direction. So what does that mean? Here it's 0. On this side it's positive. Here it's all negative, and here it's positive. So the derivative is going to look like this, roughly. Okay, so that's the kind of thing that you need to be able to do. But I won't ask you, okay, figure out the derivative and then tell me what's going on in the graph. That's coming up next unit. Okay, but I will talk about it with you, because I think the more we talk about it, it'll be easier in the next unit. All right, I'm going to leave it there for today.